Hi, welcome to videos on control system compensation. So in this video we'll see one more design of designing a compensator. So this is the transfer function or the block diagram of the transfer function, having a line transfer function as 1 over s into s plus 1. DFS is the compensator block diagram. So we are supposed to design this particular compensator keeping these two things in mind. So the lead compensator should provide a phase margin of 40 degrees, greater than 40 degrees, and the steady state error should be less than 0.1 for a unit ramp input. For a unit ramp input, steady state error should be 0.1. So these are the two specifications that are given for designing this lead compensator. Okay, in this entire series of compensation videos, we are concentrating only on the lead compensator. We're just looking at, okay, how do we design it. Maybe in one of the video we just see which particular type of compensator is chosen for a given problem. So in this case we are assuming that we are straight away going with design for a lead compensator. Okay, for this particular problem, since the steady state error is given as 0.1, that too for ramp input, so ESS steady state error is given by 1 over kV. So since we know ESS is equal to 0.1, so naturally kV happens to be 10. So since we are considering DFS as k, so naturally k will be equal to 10, which will give a steady state error for a ramp input as 0.1. So with this k is equal to 10, if we actually find out what is the open loop transfer function with DFS into GFS as 10 by s into s plus 1, we get the magnitude expression as given over here. So from this we can find what is the gain crossover frequency. Theoretically it comes out to be 3.08 radian per second, and the phase angle equation is given over here, and since it has got only two poles, the phase crossover frequency is infinite. You can actually find out the phase of this particular plot at omega equal to omega GC as minus 162 degrees. So from which we can find the phase margin, which is coming out to be close to 18 degrees. Of course the gain margin is infinite because omega PC is infinity. So let us go to 20 sim and try to verify whether the phase margin is 18 degree or not, and we'll also see whether the gain crossover frequency is 3.08. Okay, let us do the simulation using 20 sim. I have already edited the poles over here. One pole is at origin, the other pole is at -1. The system gain is 10 over here. So with these specifications, let us see what is the Bode plot of this. This is the Bode plot. You can see the phase margin is 17.95 degrees, and the frequency, that is omega GC, is 3.08 radian per second. So which is exactly the values we obtained in theory also. You can see in theory we got the omega GC of 3.08. You can see it's almost 3.08, and the phase margin is 18 degrees. You can see it is 17.95. This is 17.95. The corresponding frequency at omega GC is close to minus 162 degrees. So you can see this dot line corresponds to minus 162 degrees. So this way we can able to verify whether the phase margin what we found using theoretical equation is it same as that in the simulation. They're exactly matching. So let us proceed with the design of the compensator. This is actually without compensation by considering D of S as only K. We not considered any poles and zeros of that compensator network. We'll consider that and then try to revisit the simulator to get that design. Okay, now we will proceed now with this compensator requirement, because we know that after putting that compensator we are supposed to have a phase margin of 40 degree. So we know that this phase lead network will shift the gain crossover frequency to right side when it is put on the system. So even though we already have 18 degree phase margin, what we required is 40 degree. So remaining 22 degree has to be provided by the phase lead network. So in order to account for that additional shift in that omega GC, we are having another 5 degree being added onto the requirement. So it comes out to be 27 degree. So let us have close to 30 degree as the phase introduced by that phase lead network. So for this particular 30 degree, we are trying to find the value of alpha, which is the component which is one of the important parameter that need to be found for designing a compensator. So which can be found by knowing what is the maximum phase shift. Since we want to have a maximum phase shift of 30 degree, which is phi m, which can be seen in this phase plot also. This is the magnitude plot of the phase lead compensator having 0 dB till the point where the 0 comes. So once the 0 is there, you can see there is a positive slope, and then there is a pole comes, and again the slope becomes 0 dB per decade. So with this maximum phase shift required as 30 degree, we are getting alpha as 0.33. So now let us try to see. So at this particular frequency where it is giving maximum phase shift, let us try to find out what is the magnitude of this magnitude plot. So at this particular frequency where it corresponds to maximum phase shift. So that can be found theoretically, which happens to be 1 over root alpha, because we already know the value of alpha is 0.33. We can actually certainly find this value. So this comes out to be 1.74 in terms of value. The dB of that is 4.8 dB, meaning at this particular frequency, this is going to have a magnitude of 1.74 or 4.8 dB. Suppose if this is in terms of dB, then at this particular frequency it will be 4.8 dBs. Now we know that this is having a positive slope, and the magnitude is 4.8 dB. Since it is put in cascade with the actual plant block diagram, so we are supposed to nullify this 4.8 dB from that actual block of GFS. So now what we are trying to do is we are trying to identify a frequency that corresponds to opposite of this 4.8, that is minus 4.8. So this particular frequency happens to be the frequency at which our maximum phase shift should occur, which happens to be in this particular case. So you can see I'm substituting this minus 4.8 dB. The equivalent of that in ratio is 0.575. I'm equating this magnitude to this magnitude equation. So magnitude equation of GFS is given by this, and you equate this to 0.575, which corresponds to minus 4.8 dB. Now you can see this is the frequency at which this happens. Now this frequency will be the new gain crossover frequency of the cascaded system, which is DFS into GFS. So this will be a new gain crossover frequency, which also is the frequency corresponding to maximum phase shift. So using this 4.11, we can actually locate the 0 and poles of this compensator network using these equations. You can see you can actually find the 0 and pole frequencies. So using these equations, since you know omega c, which is the center frequency at which maximum phase shift will occur, so as we saw in the previous plot, now this is that frequency which is 4.11. If you know this as 4.11, then we can find what is this frequency, what is this frequency, since you know the value of alpha. So that is what we are finding here. So 0 frequency is coming out to be at 2.36, below, of course, lesser than omega c. Omega p certainly, which is omega c by alpha, which comes out to be 7.15 radian per second. So since we know the position of poles and zeros, so we can actually incorporate these two values into the transfer function, because now you can see this is the pole 0 representation of that transfer function of compensator network. So now since we already had the value of k as 10, so now this is the time constant representation. Now this is 1 over 2.36, this is 1 over 7.15. So this is a time constant, and this is the pole 0 representation. If you can see, this is the final cascaded compensated open loop transfer function, where you have both. Okay, you can see now this is 10 divided by s into s plus 1. Now this is the value of 10, which is k, and s into s1 plus s is your GFS, and this particular term, that is 0 term, and this particular pole term happens to be for the phase lead compensator. So overall phase lead compensator and GFS has got 1 0 at minus 2.36, and it has got 3 poles at these positions, and it has got a system gain of 10. So whatever 30.43 we have is the root locus gain, whereas because it is there in this pole 0 form, this is there in time constant form. Whatever constant term you have in this time constant form is called as system gain. Whatever constant term you have in this particular case 30.46 is the root locus gain, because the transfer function is in the form of poles and zeros. So by editing these poles in 0 position and the constant gain, so we will get, of course we can verify whether we are having the same kV, which is equal to 10, which will result in a steady state error for ramp input as 0.1. So since kV is equal to 10, for a unit ramp input ESS will be 0.1. So for this compensated network, the omega GC happens to be 4.12 radian per second, and omega PC is infinite. So since omega PC is infinite, we will certainly have the gain margins infinity. So we can actually find out what is the phase margin of this compensated system, because we know this entire transfer function. So phase margin is coming out to be 44 degrees. So we expected 40 degrees. So we are meeting the specifications. So what we can do is we can go back to 20sim simulator, edit the transfer function by having the poles and zeros of this compensated network at these appropriate points, that is at 2.36 and 7.15, and try to see what is the omega GC and the phase margin. So phase margin as per the calculation is 44 degrees, and of course omega GC is 4.12. Let us verify the same in 20sim also. So let us go to 20sim and try to do it. Now you can observe that addition of 1 pole and 0 corresponding to this particular compensator design. You can see 0 is at minus 2.3. This is the frequency, and its location on the S plane is minus 2.36, which is over here. Similarly, we have the pole of that compensator network is at minus 7.15, and we can see here this is the system gain, which is 10 here. You can see it is edited as 10. You can see the corresponding root locus gain is 30.3, which is over here 30.4, which is almost same. Now we have these 3 poles and a 0 for this compensator network. We can actually find out what is the Bode plot of this. So Bode plot for this will going to result in a phase margin of 44 degrees, and then we are supposed to get, I can see the phase margin is 43.8 degrees, and you can see the corresponding frequency of omega GC is 4.11 radian per second, which is exactly we got in the simulation, in the calculations also. You can see it is 4.12 radian per second omega GC, and the phase margin is 44 degrees, and what we wanted was 40 degrees. We are getting it very close to it. So let us also observe one more thing, that is whatever we saw in this case over here, that is this 4.8 dB. So let us edit only the compensator transfer function, that is poles and zeros of the compensator, and try to see at that frequency of 4.11, so is the magnitude is 1.74 or not. So let us go back to this editor and then try to have only the poles, and okay, let me just edit this, and let me remove this. Let me remove this also, and let me have that. Let me have the system gain as 1 and try to see. So it's done now. So let us see what is the. So we are looking at 4.11 radian per second. I have had it as 1.74 as the magnitude. You can see now this. Let us see what is the corresponding phase. So we are supposed to get a phase of, since we are looking for maximum, okay, fine. You can see maximum phase that we are expecting from this phase shift network is 30 degrees. You can see you are getting it 30 degrees. That's what we started with, and the corresponding frequency is 4.108, almost close to 4.11 radian per second. We can actually see what is. Okay, this is the location corresponding to maximum phase shift, and you can see here, since this is in dBs, you are looking for 4.8 dB at this point. You can see